All right, we're going to do some practice problems with parametric equations now. And if you hear music in the background, it's because my wife is on a conference call in the other room, and I didn't want you guys to be too distracted by whatever background noises there are, so just playing some chill music instead. You cool cats and kittens. Thumbs up for anyone who gets the reference. All right, so we're continuing on in eliminating the parameter, which is another way of just saying that we are going to find a way to rewrite the set of parametric equations as a rectangular equation. And we have our first exposure to working with some equations that actually deal with theta as the parameter. In other words, x is a trigonometric function of theta, and so is y. Y is equal to 4 sine theta. So both x and y depend on some angle. Now, previously I said our job is to try to isolate our parameter. And I'm going to encourage you actually not to do that here, because in trying to isolate theta, we end up working with some inverse trig functions, which could just make our lives pretty complicated. So I'm going to have you kind of simmer and think about what else I could do that might connect x and y without having to use any inverse trig functions. So we'll get to that in a moment. But first, let's actually take a look at what our parametric equations result in, what kind of graph we get here. In other words, what's our plane curve? So first step, again, is to go ahead and set up a table. So we've got theta, we've got x, and we've got y. And I didn't give you an interval for theta. I should do that. So let's say theta are values between 0 and 2 pi. What I didn't give you also is the step for theta. In other words, okay, so how many degrees or radians apart should I be checking values for? Are you talking about every 1 degree or every pi over 4 radians? And let's not overcomplicate it. Let's just go every pi over 2 radians. So we'll start out with theta being equal to 0 radians, then pi over 2 radians, then pi, then 3 pi over 2, and then 2 pi. All right, so you'll notice these are all just the quadrantal angles. So now let's figure out what x and y are for each of these values of theta. So when theta is equal to 0, to find x, we would say cosine of 0, which should just be 1. Okay, and if you haven't already done so, now pause and see if you can fill out the rest of this table. If you did so, you should get the following: 0, -1, 0, and then 1. For our y values, we should get 0. And since we're working with 4 sine theta, we're going to multiply all of our outputs by 4. We should get 4, 0, -4, and 0. Now let's actually look at this plane curve. Let's graph it. So I'm going to go ahead and draw that better. And let's fix that a little bit just so it looks a little straighter. Okay, and our x values go from -1 to 1, so that's why I didn't need to make my x-axis too wide. And my y values go from +4 all the way down to -4. When x is equal to 1, I get 0. When x is equal to 0, I get 4. And just plotting the rest of the points, we should get something that looks a little bit like this. And not the best looking curve there, but you get the idea. And ask yourself, what's the final thing that would be missing from this graph? And you would be right. We need to indicate the direction in which theta is changing. So at the point 1, 0, theta was equal to 0, and we're actually moving around counterclockwise in the same way our angles would increase on our unit circle, and there would be our direction arrows. Now, looking at that curve there, that should get you somewhat intrigued about what's going on here. And hopefully, we can see exactly what's happening there. So now let's focus on eliminating the parameter. And I'm not sure exactly what's going on with my Apple Pencil here, but here we go. Okay, so the question that I posed at the beginning was, how can I find a way to connect x and y without necessarily isolating theta? I don't want to get theta by itself because, again, that's going to result in inverse trig functions, which would make our lives a little difficult. Instead, how can I find a way to come up with a rectangular equation, an equation that deals exclusively with the variables x and y, while eliminating theta, so that theta disappears, but we still get some type of equation with x and y? Let's write the equations again. So x is equal to cosine theta, and y is equal to 4 sine theta. And perhaps if it might make your life a little bit easier to think about, say cosine theta is equal to x, and sine theta is equal to y over 4. Well, why did I write it that way? Because hopefully now I can get you thinking about asking yourselves, what do I know of? What relationship do I know of between cosine and sine? And hopefully you saw, or hopefully you realize, we know of the Pythagorean trig identity, which says that cosine squared theta plus sine squared theta is equal to 1. It's the Pythagorean trigonometric identity. Well, what is cosine theta? You see here, cosine theta is just whatever x is. So instead of saying cosine squared theta, we can say x squared. Well, what is sine theta here? Sine theta is y over 4 plus y over 4 squared, and that's equal to 1. And this is where you should be getting really excited, because if we have just eliminated the parameter, how did we do that? We eliminated theta. We eliminated our parameter theta. Remember, x and y were both dependent on our parameter theta. Now theta is gone. Now what we have is an unsimplified form of this rectangular equation. X squared plus the quantity of y over 4 squared equals 1. If I clean that up a little bit, notice what we get. X squared plus y squared over 16 is equal to 1. Does this at all look familiar to you? And yes, we have the standard form equation for an ellipse, which is exactly the type of plane curve that we got when we graphed this. So we have our rectangular equation, x squared over 1 plus y squared over 16 equals 1. And that confirms what we had as a plane curve just by sketching our plane curve using our parametric equations. All right. Now we have a slightly more challenging problem where we have to eliminate the parameter. And again, if you haven't already done so, take a moment to pause the video and give this a go. See what you can do to eliminate the parameter. So it turns out there's a couple of different ways to do this. One that requires a little bit more legwork, and the other one that I think is a little bit more nuanced, but a lot of fun. So if you went ahead and sat here and wrote this and wrote, okay, x is equal to e to the 3t, and ask yourself, what can I do to isolate t? What can I do to get t by itself? And the fact that we're looking at one side being e to the 3t power, the answer probably lies in the fact that we want to take the natural log of both sides. And the reason why this is so great is because if we take the natural log of both sides and one side has e, review your logarithmic properties. If we take the natural log of e raised to the 3t power, that can just be written as natural log of x is equal to 3t. And that allows me to just say t is equal to 1/3 natural log of x. And if you're having a hard time wrapping your mind around that, again, review your logarithmic properties, okay? And just ask yourself, what would that look like if I were to expand that in its full logarithmic form? Maybe another way of writing that is to say something like this. Log base e of x is equal to 3t. Take a moment and think about that. Now, once you have t is equal to 1/3 natural log of x, we then want to just substitute t into the other parametric equation. So y is equal to e raised to the 1/2 and then y is equal to e to the 1/6. If I just do some basic algebra here. X, and then y is equal to e raised to the ln, and I'm going to use some log properties to basically move this coefficient and raise it to a power, x to the 1/6. And again, you're going to need to use and revisit your log properties to think exactly about what's going on there. But ask yourself what happens when I have something with a base of e and I'm raising it to the power of something with a natural log in it. But you should get y is equal to x to the 1/6 power. Okay? And if you remember what I said initially, I said there was more than one way to do this. My alternative method, which doesn't require the use of logarithms at all, is to go ahead and just take this first equation and rewrite it so that it's x is equal to e to the t power, and all of that raised to the third power. That's the exponent power properties. Well, if that's the case, if I were just to take the cube root of both sides, I would get e to the t is equal to x to the 1/3. Well, why on earth would I do that? Because I could take my other equation and rewrite this so that this is well, what's the point? What's the use in that? Notice I've got e to the t power right over there. So if I substitute now, I can say y, plug that in, y is equal to x to the 1/3, and raise that to the 1/2 power. And we get exactly the same thing. Okay? So, doesn't use any logarithms at all, but I liked it a lot. All right, final problem for this lesson. The final problem is now to actually do the opposite of what we've been doing so far, which is to take rectangular equations and rewrite them in parametric form. And honestly, this is probably going to be the easiest thing that we do in a while. Here we are given a rectangular equation, y equals 4x squared minus 3, and we're going to come up with a set of parametric equations. So in other words, I want to come up with an x equation and a y equation. Well, don't make this any more difficult than it needs to be. There is no rule that says that your x equation has to be anything super complicated. Why can't we just let x be some function of t? Specifically, let x be equal to t. And yes, it could be that easy. Let x be some function of t. Specifically, let x be equal to whatever t is. If that's the case, what does y have to be? Y is going to be, using the same rectangular equation that we have up here, y is going to be equal to 4 times x squared. But if x is just t, then we can say let y be equal to 4t squared minus 3. And yes, it can be that easy. But Mr. No, what if we want to make this even more difficult? Well, sure, let's spice things up a little bit. Let's say let t be equal to x plus 1. In other words, let's let x be equal to t minus 1. And all I'm doing there is rewriting x in terms of t. Well, if x is equal to t minus 1, then y is just going to be, again, 4 times the quantity of t minus 1 squared minus 3. And if we just simplify that a little bit there, we can say y is equal to 4 times quantity of t squared. Let's clean this. Let's do this here. Minus 8t plus 1. Yep, that should be right. So here are my two parametric equations. And that's all there is to that. So hopefully parametric equations make some sense to you. Just know that we're shifting from working with rectangular equations, like we had up here, to working with parametric equations, which is just another way of expressing the same equation. All we're doing now is we're expressing both our variables x and y as functions of some other independent variable, which we call our parameter. And we can go both ways.